Hello, everyone. Welcome to our live stream. We are excited to have you here today. I'm having some technology issues, so I'm going to try and mitigate those, and we will forge ahead with our stream today. We are excited to have you here. My name is Matthew. I work for Professor Impey and do a lot of the behind-the-scenes stuff on the class. And I will hand this over to Chris to say hello and good morning, and then we will get started with your questions.
Okay, good. So it's a little after time, so I'll just get started straight away. Welcome all of you from the online class or just people who have found out about this Q&A session, ready to take your questions.
Excellent. The first question is from Hamid, who's on with us live. How is everything particle in the universe in unstable equilibrium and having the possibility of decay? So why do particles just spontaneously decay? It seems like the question.
Okay, that's a good question. That's a sort of fundamental physics question. Not everything in the universe decays at the level of fundamental particles. There are particles that we believe are stable and eternal, if you like. For instance, electrons, this would be an example of that. However, it is true, and can be true of the light particles or the leptons in the standard model of particle physics. However, it is true in grand unified theories of particle physics. Some of the baryons, the heavy particles, in particular the proton, is not long-term stable. Proton is, of course, made of individual quarks, a triplet of quarks. And in these theories, which are not yet fully verified, the proton has a very long decay lifetime, maybe 10 to the power 35 or 36 years. It's not yet been detected. So in a sense, the reason for these particle decays, some particles decay for various reasons. For instance, radioactivity is a phenomenon where an atomic nucleus decays by transmuting protons and neutrons, losing energy, and the large atomic nucleus can become a smaller atomic nucleus. So that's a decay that happens in an atomic nucleus. But individual fundamental particles can also decay. They can have very short decay times, tiny fractions of a second, or exceptionally long decay times, billions or trillions of years. And the reasons for this are actually profound, and I will not claim there is any fundamental theory of physics that fully explains why some particles decay and other particles don't. It's presumably related to a more profound theory of particle physics beyond the standard model that we have now. Just as the generations of particles and their individual masses, although the masses come from the Higgs mechanism, the reasons the masses are what they are is not prescribed by the model, and nor are the decay modes of the various particles. So this is actually still a mystery of fundamental physics.
All right, the next question is from Hernan, who asks, seeing as there's not a snowball's chance in a hot oven that we'll be able to send any probe or dragonfly missions to even the closest of exoplanets, why don't we concentrate our efforts and limited budgets to searching for life 2.0 on the moons in our accessible solar system? So why not focus on those close up?
Well, there are some quite ambitious missions within the solar system. And the simple answer is feasibility and cost. Remote sensing exoplanets, just using light as the carrier, is cheaper, easier, and quicker than sending probes to the outer solar system. The minimum price tag on any plausible next generation probe we have the Europa Clipper, but behind that is a Europa lander. There's a mission for Titan, the Dragonfly mission alluded to in the question. There's also a very ambitious mission which would be privately funded from Yuri Milner to sniff and even sample return from the icy jets of Enceladus. So these are three sort of life-sensing missions in the outer solar system with price tags of, the Milner mission claims to be only a few $100 million, but the other two will be several $1 billion. NASA only has the free energy to do one outer solar system mission at a time, essentially. So you're immediately looking at a 10 to 12 year time frame for these missions and to return their data, another 5 to 10 years. We're going to be sniffing exoplanet atmospheres within a couple of years with the GMT, with the ELT, and then eventually the TMT, the three large telescopes planned. So most people, if they're placing bets, are going to say that the best odds of finding life beyond Earth are going to come from those exoplanet experiments, and on a much quicker time scale, at least a decade before anything in the outer solar system.
Excellent, thank you. The next question is from Isla, who asks, when will the expansion of the universe exceed the speed of light?
That's an interesting question, because the acceleration of the expansion does imply that at some point it will exceed the speed of light. And in fact, that time is not that far off. It depends on the amount of dark energy. It also depends on the nature of dark energy. We know what the proportional contribution of dark energy to the cosmic expansion is. It essentially provides 2/3 of the cosmic expansion, and retarding the expansion is about another 1/3 from dark matter, or closer to a quarter. But how that actually progresses with time depends on the nature of dark energy itself, and we don't really have a fundamental theory of dark energy. But just assuming it's the simplest form that doesn't vary over time and space, which is like Einstein's original cosmological constant, then it is a prediction that in 3 or 4 billion years out, there will be parts of space-time that are expanding faster than light speed. And at that point, we'll lose sight of those regions of space-time. And gradually that region of accelerating expansion will close in on, at that point, the merged Milky Way and Andromeda combined galaxy, and that'll be all there is. So we will lose the extragalactic universe because of this accelerating expansion. So we better enjoy all those galaxies we can see with our big telescopes, because with dark energy, that's not going to last forever.
Excellent. The next question is from Dr. Astronomy, who is on with us live and asks, my question is about the color of astronomical object images. Are the colors real, or have they been made by the data processing software? For example, images from the Hubble Space Telescope and radio images.
So in general, there is modification of the colors. It's unusual to see true natural colors of astronomical objects, and that's really because the colors are actually quite subtle. NASA set out on this decades ago when we were exploring the solar system, and they started amping up the colors and making Mars redder than it really was, and making the giant planets more orange and yellow than they really are. They're actually very pale, their colorations. So solar system images for decades have been amped up in their colors. Not completely manipulated and made false, but definitely exaggerated by a large amount. Radio images are a completely different matter, because there we're dealing with non-visible radiation. Our eyes are not sensitive to radio waves, so essentially you have to apply a color table or a grayscale to the image just to represent it visually. So almost by definition, any image at X-ray or radio wavelengths or beyond the visible spectrum is an artificial color table, and the colors are essentially arbitrary. There is a tradition in astronomy at non-visible wavelengths to make the blue be the hotter regions and the red be the cooler regions, which is essentially mirroring the way that photons go in the visible spectrum. As far as Hubble images, they made an effort in the project pretty much from the beginning to try and be as realistic as possible. So they're not completely realistic, what your eye would actually see if you were looking through the Hubble Space Telescope, but they're close. So they try and make a color balance that roughly represents the sensitivity curve of the eye. And so Hubble images, while there may be some color enhancement or exaggeration, there's quite a good fidelity to astrophysics in that. And that means when you're looking at some nebula regions and you see pink glowing regions, that does represent the H-alpha emission line of hydrogen, which is at 6,500 angstroms. And when you see glowing regions that have this greenish tinge, that does represent an oxygen line of emission at about 4,300 angstroms in the green part of the visible spectrum. And so that means you can look at Hubble images and actually see some of the astrophysics that's going on.
The next question is from Jeffen, who asks, why hasn't the Earth fallen down into the sun because of gravity?
Well, the Earth is in a gravitational balance. So being in a stable orbit, it means that the kinetic energy of the Earth in motion as it moves around the sun, as it does its orbit every year, is balanced by the gravitational potential energy, which is the pull of the sun's gravity. And those vectors balance out. There's the inward vector of the pull from the sun, and then there's a translational or tangential vector of the Earth's motion. And these two forces are in balance, and that's why the orbit is stable. Now, in some orbital situations, over time, the orbit will decay, and that balance will be broken. For example, if the object orbiting a star experiences drag, perhaps it moves through dust clouds or gas clouds, and that drag causes it to slow down, then at that point, it will start to spiral in towards the star. But in our situation, space is essentially empty, so the Earth's orbit is very stable for long term, for billions of years, basically.
The next question is from Pinoclean. Excuse me. I would like to hear Professor Impey speak about galaxies without black holes. Can you talk about whether there are any, and if so, why or why not?
This is an interesting research area right now because it has been a premise of the last few decades, as we found black holes in more and more galaxies, that every galaxy has a black hole. It's just a feature of a galaxy, because the mass of black holes for the hundreds of galaxies where they've been seen is proportional to the old star mass in the galaxy. So typically for a spiral galaxy, that would be the bulge mass. And for an elliptical galaxy, it's the entire mass, and therefore the black holes are much bigger. So this scaling applies over orders of magnitude, or a factor of 10,000 in galaxy mass and black hole mass. And it seems to be a pretty well-held situation. However, there have been cases where black holes have not been detected. Now, typically these are in lower mass galaxies. Every massive galaxy found so far is seen to have a black hole. Now, occasionally the centers of large galaxies are obscured by dust or gas, or they're just very difficult to study at high enough resolution because the galaxies may be far away. And so sometimes we simply don't have good evidence of a black hole. But the limits are such that we can't say the black hole is not there. But there are some cases of nearby dwarf galaxies where there doesn't seem to be a black hole, and we might expect one based on the scaling between black hole and old stellar mass. And this is still a matter for debate, whether galaxies can form without central black holes. Another possibility is that the black hole may be ejected. Galaxies, of course, grow by mergers, and if each galaxy has a black hole and galaxies merge, it's entirely possible to have a gravitational slingshot mechanism where an interaction causes one of the black holes to be ejected and the other maybe not, and so you're left with two galaxies, one of which has a black hole and the other doesn't. So sometimes interactions could eject a massive black hole from the center of a galaxy, but that's a pretty rare effect. So this is still an active area of research.
The next question is from Tian, who asks, could simple life be briefly or long-term created during the collision of two comets, giving the diversity of complex elements, the energy from the impact, and the possible existence of liquid due to the collision?
So comets' role in biology and life is interesting and occasionally controversial. The amount of heavy elements, the amount of complex molecules in comets are interesting, and they also have a lot of frozen water. So comets do indeed have a lot of the ingredients for life, and it is thought that cometary deposition of water and organic material could have been part of what seeded life on the Earth, since there were a lot of impacts from solar system debris, including comets and asteroids, early in the history of the solar system. If two comets collide, then their material combines. Clearly there might be enough energy for that icy material to become liquid for a while. The trouble is, most models of those kind of collisions do not suggest that the water would be liquid long enough for interesting interactions to happen, and therefore to build more complex molecules in life. The process whereby the building blocks of life, which do exist in comets, grew into the first replicating molecules in the first cell, nobody knows how long that took, but it almost certainly took longer than a few million years. And that is a process that simply could not take place in a comet, in a colliding comet. You wouldn't have suitable conditions for long enough, basically. So people are not currently of the opinion that comets could harbor life by having had collisions or just on their own. but they are definitely play a role in the development of life and in the seeding of the ingredients for life early in the history of a terrestrial planet.
The next question is from one of our live participants. Is there an equation or a distribution type graph to determine if a planet or moon will be tidally locked?
Yes, there's a very simple mathematical formula. There's it's basically the tidal radius of an object is the distance from that object at which the differential force on the orbiting object, the smaller object, is such that it experiences a tidal locking capability. That's obviously satisfied for the moon going around the Earth and for Mercury going around the sun and so on. So yes, there's a basic mathematical formula for tidal locking. At a slightly larger level of tidal influence, there's also a limit called the Roche limit, and that's the one where the stresses on the object caused by the difference in gravity between either side of it for the larger object exceed the tensile strength or the strength of the rocky material it's made of, and the rock breaks apart. And that's where objects orbiting smaller objects orbiting large bodies will shatter and disintegrate. So there's tidal locking, and then somewhat beyond that, with a much stronger tidal force, there's actually the destruction of the object itself.
The next question is from an email. Wendy asks, is there anything humanity could do to inadvertently accelerate the sun's red giant phase?
I don't think so. So as far as the sun's fate and evolution, the end of the main sequence where the hydrogen has been exhausted, the sun will go through an unstable period, will reconfigure itself, collapse a much hotter core, and blow out a larger envelope, and at that point it becomes a red giant. The only thing that's going to trigger the red giant phase is the exhaustion of the hydrogen that's been fusing into helium for 4.5 billion years. And so the sun at the moment is barely halfway through its life as a main sequence star. And there's no conceivable way we could accelerate that process of fusion in an object as massive as the sun. So that red giant phase is still sitting billions of years away, and I don't think there's anything our technology could do to possibly advance that. It's just going to take a long time before it happens.
So it's a nice segue into Haneen's question, which is, how long does a star live? And maybe you can talk about how we know and some of those effects.
Sure. The lifetime of a star is determined by its mass. So the most fundamental quantity or parameter of any star is its mass. If you know the mass of a star, you can pretty much decide its fate, its lifetime and its fate. And that's because the mass determines the configuration the star will take, the balance it will have between gravity pulling inwards and pressure from fusion reactions pushing outward. And that balance creates a fusion rate, and the fusion rate combined with the mass of the star, how much fuel it has, tells you how long it will last. And the nature of that relationship is that star lifetime is very strongly dependent on mass in an inverse way. And it goes as almost as the 2.5 power of the mass, minus 2.5 power of the mass, which means that a very massive star lives a much, much shorter lifetime than the sun. The most massive stars, 50 to 80 times the mass of the sun, have lifetimes that are just a couple of million years. The sun has a total lifetime of 10 billion years as a main sequence star, and a star that's at the limit of fusion, the cool limit of fusion, red dwarf star, about 10 times less massive than the sun, could live 10 times longer than the sun. I mean, have a lifetime of actually 100 or 200 billion years. So there's an incredibly strong dependence between lifetime and mass.
Excellent, thank you very much. The next question is from an email. In light of new discoveries of Hycean mini-Neptunes that might harbor life, do you think that the focus on Earth-like Goldilocks planets for life has been too one-sided, and also that life outside Earth is overwhelmingly likely to be microbial?
Right, so there are two different questions there. There are, as the questioner implies, new categories of planets that have potential for being habitable and harboring life. Mini Neptunes, for example, and super Earths, examples of neither of which exist in our solar system, turn out to be the two most abundant categories of planets. I think fully a majority of all the exoplanets are one of those two categories, and a very relatively small fraction are actually Earth-sized or smaller, or Jupiter-sized or larger. So these are the large categories of planets, and there's some evidence based on simple modeling that they could be habitable, some fraction of them, probably not all of them. So yes, I agree that the sort of concentration on Earth clones or Earth-like planets has been a little overdone. It was understandable when we were seeing bizarre and really extreme exoplanets that were clearly uninhabitable to try and look for similar situations to the Earth. But now we have a lot of other exoplanet possibilities that are quite likely to be habitable, and I think attention is starting to turn to those. As for the nature of the life on any exoplanet, yes, the most likely form of life anywhere else in the universe is microbial, because that is what the Earth started with, and that's what the Earth still has most of. If you look at the tree of life and the genetic real estate of life on Earth 4 billion years after life started, roughly, you'll find that most of the genetic real estate is in microbes, not in plants and animals, or the larger creatures on the Earth of any kind. So this is still a microbial planet, as it was since the beginning, and we have every reason to expect most of the exoplanets with life will be microbial worlds, and maybe only a small fraction will ever have developed large life forms.
Excellent, thank you. I just want to remind everybody real quickly that we do jump around questions. Please post your questions in the chat as you've been doing. We grab the questions from that chat, but we also jump around. So just ask your question once. I try to make sure that everybody gets a chance to get a question in, and I try to go in order, but I also move around to make sure we get a good variety of topics. So if I haven't gotten to your question yet, I will do my best to get there, but it's just me filtering through all the questions, so I appreciate your patience. The next question is from, sorry here, let's see. So Varsha would like to know about how does one become an astrobiologist? They've completed a bachelor's in geology. What's the path to becoming an astrobiologist?
So astrobiology is a very interdisciplinary subject, and if you have an initial training in geology, that's a pretty good start. So astronomy and geology are almost equally good starting points to do astrobiology as a graduate student, for example. The missing ingredient is of course biologists. Most astronomers doing an undergraduate degree in astronomy or physics and astronomy don't take biology classes. So it's very unusual to find an undergraduate program in astrobiology. Most of them, almost all of them, are graduate programs. So what you're looking for, of course, is a program that will include maybe the astronomy you haven't had if you were doing geology, and then include a good dose of biology. It's challenging, if you didn't do an undergraduate degree in life sciences, to take graduate level or close to graduate level biology courses, but astrobiology programs figure out a way to do that and give people a good grounding in biology. The other areas you might study, of course, would be planetary science. So some planetary science departments offer astrobiology. University of Washington is a good example. They've had an astrobiology certificate program for a couple of decades, and now a PhD program too. And they sample program or courses from their biology departments, from their geophysics department, and so on, and they mix and their astronomy program, of course. So you'll get a mix of classes as an astrobiology student, and essentially it's the master's level training, 2 years of coursework, that give you enough biology to be a professional astrobiologist later.
Excellent, thank you. Isaac, who's on with us live, asks, what would an astrophysicist work with now? And I believe the clarification is, what kinds of things are astrophysicists working on now, and what are some of the cutting edge topics or fields that astrophysicists are studying and most interested in?
So in astrophysics, the areas of interest, they haven't changed dramatically in the last 10 or 15 years, but I would say cosmology has always been of interest, intense interest to astrophysicists. because now we're homing in on a model of the universe. There are extremely large data sets of surveys of galaxies. There are all-sky surveys at optical, radio, infrared wavelengths. We know the contents of the universe pretty well. And so astrophysicists are working a lot on theories of how the universe got to be the way it is, using simulations in particular. So there's a lot of simulation work. So that's a big thrust. Black holes and neutron stars, compact stars, basically compact objects. That's another very hot area of astrophysics, because the physics of that is very interesting. It's frontier physics as well as being relevant to astronomy. So the people who study neutron stars, white dwarfs, and black holes are having a lot of fun, and the techniques are advancing, and there's a lot of people working in that field. Those are probably the two hottest fields at the moment in terms of number of people working on them. But there's also more traditional work going on stellar evolution, on how stars form. So star formation is another field of astrophysics that's very popular now, because we don't have a simplified model of star formation, because it's extremely messy, complex 3D process involving magnetic fields and shocks and a lot of nonlinear physics. So that's a very rich area too for study and for making progress. So those are three of the hot areas of astrophysics, if you like, right now.
All right, the next question is from Ramani Ranganathan, who asks, is there a mass limitation to the black holes that are devouring stars and other celestial objects beyond which they can't grow?
That's an interesting question. We don't fully know the answer to that. Remember, there are essentially two categories of black holes. There are black holes that result from massive star death, and one of the surprises of LIGO and the Gravitational Wave Observatories is that some of those black holes are more massive than we would have a reason to expect. When a massive star dies as a black hole, it's gone through a violent and short life where it's lost most of its mass. So the kind of star that leaves behind a minimal black hole of 3.5 times the mass of the sun, that's just over the boundary with a neutron star, that star probably started out 15 times more massive than the sun. The surprise has been that with LIGO, we found clear evidence of black holes that are 30, 40, even 50 times the mass of the sun. And given how much mass stars should lose along the way to becoming a black hole, those are very massive. And so we're having to assume that these black holes were in star clusters where the black holes merged, and so we're seeing the result of multiple mergers over time to get a black hole that large. That's about the largest that we've seen. We don't know if there's a limit, because in a dense star cluster there could be many mergers happening sequentially, so maybe you could build black holes hundreds of times the mass of the sun. In the larger context of the nuclei of galaxies, the biggest black holes we found are associated with the most massive galaxies. I think the record holder is roughly 20 billion times the mass of the sun in a giant galaxy a few billion light years away. And we think in that case there is a natural limit, because there's only been so much cosmic time for black holes to grow, and galaxies have a maximum size. And so that implies that black holes will also have a maximum size, and perhaps we're already seeing it.
The next question is from Krakrasivo. I'm not sure if I'm saying that correctly. Is it possible to predict if an exoplanet will go rogue in a distant star system? And if so, how do they do it?
So rogue planets or rogue exoplanets are essentially free-floating planets that have escaped their star and are just traveling through space as unattached objects. It is certainly possible, and we've now detected, several surveys have now detected rogue exoplanets with some confidence, and they're projecting to very large populations of them. Of course, rogue exoplanets are very hard to detect because they have no star nearby. So the two primary methods for finding exoplanets, the transit method that the Kepler satellite used and the Doppler method that ground-based telescopes use, they don't work because there's no star that the planet is orbiting. Essentially, the only technique that works for finding them is microlensing. So it's a lensing method where the rogue planet causes a momentary or temporary brightening of a background star, and we can infer its mass from that. And we see it's a dark object, so we know that it must be an exoplanet. So that's how exoplanets that are rogue have been found. How they're created is fairly well understood, because early solar systems are unstable. Even our solar system was unstable. And in the beginning, possibly some potential terrestrial planets were actually ejected before the planets stabilized that we see around us. And they moved in their orbits anyway after formation. So early solar systems are dynamically unstable and chaotic, and it actually is quite easy to have simulations where you eject one or more exoplanets from a single system. And that's led some predictions to be that there are as many rogue exoplanets as there are exoplanets bound to their stars.
The next question is from Rostaman, who asks, is it possible that time could be a relic of human experience, so a perceptual dimension rather than something that is sort of real in the universe?
It's an interesting question, and clearly time does have a psychological dimension. It does have an aspect that's related to our everyday experience, because we experience the moving arrow of time, the fact that events unfold and we are unable to go backward and revisit something that's happened. So time is unspooling in an irreversible way. That's the human experience. In nature and in the universe and in physics, that's not always the case. At the level of fundamental particles and their interactions, time is a reversible arrow in the sense that a particle interaction that plays forward in time one way can be seen to play backward in time. You can make that happen, and it happens naturally. So time as an arrow does not exist in all aspects of nature, especially at the fundamental level, which makes you wonder, is it indeed a matter of perception? It's also connected time with the idea of entropy and thermodynamics, that complex systems tend to evolve towards disorder, to the most abundant state, which is a disordered state, and that tendency over interactions and complexity over time is what leads to the arrow of time in a complex system. So it's not purely a psychological effect. And also there are elements of time that are truly independent of our sensing of them. Atoms and particles can be tiny little oscillators, and you can keep time with these. That's what atomic clocks are, and molecular clocks. And so that timekeeping in nature is independent of our perception of it. These phenomena actually exist, and they can be measured. They can be measured by other species on other exoplanets that aren't us, so it's independent of it being human. So I think there is a component of time that's independent of our experience.
Excellent. The next question is from one of our live participants. Guy asks, is the fact that we haven't encountered any form of life elsewhere so far because there is none, or because we don't have the tools to detect it?
That's an important question that people are very actively debating. It's not clear that our sensitivity to detecting life is so good at the moment that we should draw any strong conclusion from the fact that we haven't detected life. For example, in our search for life in the solar system, we've just very started poking around. There could well be life under the Martian surface in subsurface aquifers. We're almost certain there's liquid under the surface of Mars, but it's so far down that none of the very simple drilling and digging tools of the rovers and landers can get to it. So that's an example of how we could have a planet like Mars, which has life right now under the surface that we actually can't access. And around the solar system, it's the same issue. We've just done very limited experiments. In terms of understanding exoplanet life, same thing. The experiments to detect life, which is usually means the alteration of an atmosphere by microbial metabolism, those experiments haven't really been conducted on terrestrial or Earth-like planets because they're just too hard. They will become possible soon, though. So I think the most likely answer to the question is that we are not yet able to judge the abundance of life in the universe because the experiments are hard, our searches are in their early stages, and the fact that they've failed so far is does not let you make a very strong conclusion.
The next question is from one of our live participants. Apart from how theory describes it, how do we know that gravitational waves travel at the speed of light?
We don't. We haven't done a time of flight experiment, if you like, of gravitational waves because we see the gravitational waves as they reach us and we infer the source of those waves And of course, for many of the gravitational waves, those sources, those merging black holes, are billions of light years away in a distant galaxy. And so we can't say contemporaneously, we have no contemporaneous way of saying what the trigger of those waves were. We have to use the light that comes to us, and we use our model of the layout and expansion of the universe to infer how long ago and how far away that happened. So the detection of gravitational waves from distant objects does not in and of itself tell us about the speed they traveled. The only thing that perhaps does indirectly is the time of flight between gravitational waves to different gravitational wave detectors. For example, we've seen directly in the very first gravity wave detection in 2015 that the signal reached one of the detectors, the two detectors on the opposite sides of the continental United States, one in Louisiana and one in Washington State. And the time of flight difference of arrival of those waves between those two sites was measured to be 7 milliseconds. And that's, of course, consistent with gravity waves traveling at the speed of light. So that's probably the best evidence we have that gravity waves do actually travel at light speed.
The next question is from a live participant. Shorya asks, so the general question is, what do you think is the next revolutionary step for detections in astronomy? And they want to know if you think that neutrino astronomy might be that next step, sort of like gravity waves.
Yeah, in terms of modes of observing the universe, new ways of seeing the universe, obviously gravity waves were a profound transformation in our way of seeing the universe, because we actually get to see mass directly. No other mode of detection of electromagnetic radiation lets you see mass directly. It's a very indirect representation of what the stuff of the universe is doing. So that was the most profound transformation. Neutrinos is probably an important one, although neutrinos have been detected. They were detected from the sun decades ago, and now neutrinos have been detected from a handful of extragalactic objects, including a few supernovae. So neutrino astronomy is still in its infancy, and as the neutrino detectors, some of which are under the sea, some of which are in the deep Antarctic ice, as those get bigger, and they are being planned to grow in size by order of magnitude, the neutrino astronomy is probably the next one to come of age. The other type of astronomy that is also still in a relatively young stage is gamma ray astronomy, because gamma ray detection is really hard. So the very highest energy photons. There's no currently active gamma ray telescope. NASA had a great observatory that operated for 15 years or so, the Compton Gamma Ray Observatory, but it's not been operating for a long time. So gamma ray astronomy is also an area where there could be more done.
The next question is related to an earlier question about exoplanets and planets' moons. Will, you mentioned sniffing the atmospheres of nearby exoplanets with upcoming telescopes. How is it that this sniffing or these observations of exoplanet atmospheres could help us confirm life 2.0 or the existence of life on those?
It comes down to a matter of energy use and energy equilibrium. This was known, I'll give a little historical analogy for this. This idea has been in place since the 1960s and 1970s. James Lovelock, who's very well known, written popular books, and came up with the Gaia idea, the idea that the Earth and its life and its environment are in a self-regulating loop. So life impacts the Earth and the Earth impacts life, and it's a symbiotic thing. That's a very profound idea that has a lot of validity now after decades of research. Lovelock was recruited by NASA to decide on how to detect life on Mars. And he looked at the evidence of the Martian atmosphere at the time, which is a very thin, nebulous, carbon dioxide only atmosphere, and he said, well, you already know the answer, because Mars is not a dynamic planet. It's got an inert atmosphere that just indicates geological action in the past, but no biological activity. The Earth, by contrast, has 1 part in 5 oxygen. That oxygen was put there by microbes. So Lovelock's insight was that if you look at an atmosphere of a planet, in our solar system in this case, There's a dramatic difference between an inert or dead planet, which is just in energy equilibrium with the solar radiation, and a planet where there's additional energy balance caused by biological activity. That would be the case of the Earth. And so with exoplanets, we're trying to extend that experiment. And the gas that you might look for, the tracers you might look for indicating life, are obviously oxygen is a good one. That would give you sensitivity to photosynthetic-based life. But there are other biomarkers too. Methane is a good one because early Earth had life that was a methanogen-based, that had a methane-based metabolism rather than oxygen-based. So large amounts of methane are also indicators of life. And probably you'd also want to see evidence of water vapor since life needs water. So this is the rationale. And what you're really looking at is an atmosphere that's out of equilibrium, where simple geological activity, where weathering and erosion and so on, and solar energy alone cannot account for the chemistry of the atmosphere.
Well, the next question from Saib, who's on with us live, is, can we say with any certainty that any planet that has water on it is able or is likely to support life?
That's a difficult question to be sure about. We know that water, as far as we can tell, is a prerequisite for life, that you cannot have life with no water. You can have life with very little water, though. Witness the Atacama Desert. There are places in Chile where it hasn't rained for a century, and yet there are microbial life forms there. So life can tolerate very low amounts of water. It's low enough that in an extraterrestrial setting it might be hard even to detect it. The converse, however, is hard to say. If there is water, must life exist? And the answer, of course, is no. There's no reason why it has to. It's clearly possible to have a planet with water and organic material where, for whatever reason, the combinations of chemistry never led to a replicating molecule, never led to a metabolism, never led to a simple cell, and never led to biology. That's entirely possible. So, unfortunately, we can't make a strong statement. And that's why we have to do the experiment. We need to know of all the habitable spots, that is places with water, energy, and organic material, what fraction of them does life actually develop? If we develop a sample of exoplanets where we can answer that question, then we'll have gone an enormous way to understanding how abundant life is in the universe.
The next question is from David Whittlesey, who asks, do you know of any affordable technological advancements that are coming in the near future that might be accessible to the backyard astronomer?
Well, I think the obvious ones would be in terms of amateur astronomy. I think the best ones are actually going to be with infrared detectors. So CCDs are very mature, and most amateur astronomers who want a CCD can get a CCD, and it's a pretty high quality device. You know, these are multiple dozens of megapixel imagers, and you can put a simple photoelectric cooler on them and cool them to make the background low and do really quite good work. Infrared imaging has been a difficult thing. It's a much more tricky technology. Those imagers really came from the military, and they gradually worked their way into research labs, and astronomers started using them in the 70s and 80s. And even until recently, infrared arrays were much smaller than optical CCD arrays. But I actually think infrared arrays are moving fast enough in other areas of industry and commerce that they're going to be coming into the hands of amateur astronomers soon. And those will let you do some quite interesting experiments. Now, those infrared arrays do tend to need to be cooled. You can have thermoelectric cooling. That's not quite good enough. You might have dry ice, would take you a little further, and then liquid nitrogen and a cryostat or a Dewar is, of course, what professional astronomers use. And that's not an extremely expensive technology. So that would be one frontier for astronomers, amateur astronomers. And the other one, of course, is at the computing end, because a lot of work in astronomy is computationally expensive, and computers, onboard chips that do the processing in real time, and then post-processing in computers, laptops, or whatever, that's improving dramatically, exponentially still. And so that's going to map into what people who are not professional astronomers can do with fairly simple equipment.
The next question is from Azhar, who asks, can a large asteroid push a planet away from its orbit, or would it split the planet?
So if there were a hypothetical collision between a large asteroid and a planet, so let's just imagine a terrestrial planet, something of the order of Venus or Mars, which are similar sized objects, and a large asteroid. Remember, even the largest asteroid, Ceres is the largest asteroid. We're talking about 1,000 kilometers. So the largest asteroid is more than 10 times smaller than a terrestrial planet. And that means in volume and mass, it's hundreds of times less massive. So the short answer is no. An asteroid collision is unlikely either to shatter a planet like ours entirely or move it from its orbit. I guess if the trajectory of a large asteroid were just right and it was a pretty impactful collision, it could perturb the orbit long enough to make it unstable in the long term. Not immediately eject it, but make it unstable, give it a perturbation so that it became long-term unstable and eventually was ejected. But none of this would be catastrophic and immediate. This would play out over many orbits.
The next question from one of our live participants is from John Fontana, who asks, in the search for life, we have focused on finding water. Shouldn't we also focus on finding evidence of carbon?
Yes, we do look for carbon, and actually it's abundant. So water is one of the most abundant molecules in the universe. So looking for water is not very restrictive because we expect water to be found in a lot of astrophysical environments. It's found in deep interstellar space in modest amounts and in molecular clouds that stars form from, in a vaporous form. So it doesn't have to just be on a rocky body. Carbon is abundant too. It's one of the most abundant elements in the universe. It's produced, of course, by moderate mass stars and ejected into space. So carbon is pretty abundant. I think the interesting question is, might there be another basis for life that did not heavily depend on either water or carbon? So that's asking, how possible is it there could be bizarre life, and what would that be like? Sarah Seeger, who works at MIT, and William Baines, who's a biochemist, wrote an interesting paper a few years ago where they analyzed the entire universe of molecules that might be associated with life of conventional or unconventional form. They considered, I think, 14,000 molecules. And they came up with a few hundred that were relevant to life. And they were some unusual molecules in there. Obviously, ethane and methane were included because Titan has ethane and methane oceans. Ammonia is in there, acetylene. And that's a volatile ingredient. So in terms of mediums in which life might develop or ways life might build complexity, there's a very large set of molecules that we might consider, and they're not even all carbon-based. So we have to have an open mind. The trouble is, it's hard to know exactly what to look for. That's a wild frontier to wonder how strange life might be.
So the next question, it's related to a kind of a comment thread that was going on in the discussion. And the question is, why should we commit to Mars? Why commit so many resources to exploring Mars? It seems like a dead end. It doesn't seem like there's any life, that's there, or it seems unlikely. Why commit to so much, sending so many of our resources there?
Yeah, the complaint about obsession in some quarters, as it's called, with Mars, it comes in the professional community too, from planetary scientists and astronomers. Some of this is NASA's priorities. NASA has prioritized Mars systematically in its planetary exploration program. And planetary scientists are excited by Mars too. There's the very simple answer, which is practicality and cost. Mars is by far the closest object to the Earth where we might find life. It's our nearest neighbor, essentially. And Venus is a near neighbor too, but it's inhospitable, and we are going to send eventually some probes back there. So as a place that's plausible for life, where we know it was warmer and wetter in the past, and there was a very good expectation that there could have been life there 3 billion years ago, it's a neighbor. It doesn't take too long, 8 or 9 months, for a mission to get to Mars. and we have the prospect of sample return, not real soon, but within 7 or 8 years. And once you return samples from Mars, which the Perseverance rover is doing right now as we speak, it's dashed its first core sample from the J0 crater. And bringing back samples from Mars will up the game of detection of life, because you can look at those samples in gory detail, far better than any of the rovers can in situ, and look for evidence, biochemical traces of life, not actual fossils or microfossils. So it is still a good place to look for life relatively nearby. That said, other people think there should be more placing of bets in the outer solar system. Europa is a water world. Titan is a place where life 2.0 might exist because it's so different from ours. And Enceladus has these geyser jets with salty water in the interior and potentially life. So outer solar system is interesting too. But it's just far quicker, cheaper, and easier to launch a Mars mission than it is to send a mission over 1 billion miles away from the Earth to the outer solar system.
Excellent. The next question is from an email. Will the cosmic microwave background eventually be detectable in radio waves due to red shifting? And where will there come a time when it is no longer perceptible at any wavelength?
Yes, the future of the microwave background does suggest that. The universe is continuing to expand at an accelerating rate, and that means the radiation that permeates space is having its wavelength stretched by the expansion. Now, of course, the trouble is this is a very slow process taking place over cosmic time, over hundreds of millions or billions of years. So it is going to be a long time for, just to put a number on it, for the microwave background radiation to be stretched in wavelength from what is essentially millimeter waves to centimeter waves, which are true radio waves. That's a factor of 10. Then the universe will have to expand locally by a factor of 10 for that to happen. And that's not going to happen for a billion or so years. So it's going to take a long time. But if you follow this progression even further, you reach the very interesting prediction from the accelerating expansion of the universe that eventually the radiation from the Big Bang will be stretched in wavelength so much that the wavelength of that radiation exceeds the horizon, which is the distance you can see before you reach a boundary where things are moving at faster than light speed. And at that point, literally, the background radiation becomes undetectable and invisible.
Excellent, thank you very much. All right, the next question is about living on Mars. Terry has an idea about using electromagnetic waves to sort of protect things on Mars. Can you talk about what is required for plants or humans to survive on Mars? What kind, how little can we get away with supplying them, and what do we really need to have either a base or a whole civilization?
Well, I'll give one conventional idea, the standard way we think we're going to do it, and then one kind of wild idea that comes from NASA recently. The conventional way is you just have a habitat that's clad in a large layer of rock. So we have technology to take the Martian regolith, the soil of Mars, and through simple electrochemical means turn it essentially into building material, slump block if you like. And so whatever kind of dome you might build out of translucent material, you cover it entirely with possibly a meter thick of this Martian soil turned into hardened building material. And at that point, the resistance to radiation and cosmic rays is sufficient to protect all the internal inhabitants. So we're not going to be living in these nice translucent domes where you can gaze out across the Martian landscape. There may be small windows or portholes, or maybe a little observation deck where in a sheltered way you can go out for a short period of time, but you'll be getting exposure to radiation. Most of the life will be in a hardened shell, a bunker almost, whether it's underground or not. So that's essentially the way you'll have to do it. And then it means, of course, that the ventures that the Martian colonists or people on Mars make in their vehicles and their rovers will be hazardous, because that exposure to radiation will add up over time, and that will probably be their biggest risk. The radical idea proposed by a pretty senior official, I think a division chief of NASA a couple of years ago at a conference, is to go between Mars and the Sun and create, with technology, an artificial magnetic field. And there are ways with dynamos, there are ways that we have technologies to create substantial strength magnetic fields. If you could create an artificial and large and strong magnetic field between Mars and the Sun, you could essentially deflect the solar radiation, because it's of course the lack of a magnetic field on Mars that leads it to being inundated by cosmic rays and solar radiation. So this would be a beautiful solution, because that would solve the entire problem and would render the whole of Mars a safer place. Nobody's put a cost estimate on this idea. It is feasible, though. The technology is possible to do this. I'm sure it's going to be very expensive, but at the cost of, for a cost of protecting the entire planet for human habitation in a safer way, it's probably worth it.
Excellent. All right, it's 11:03. We started a little late, so I'm going to go ahead and give us a little latitude. If you have the time to go with one more final question for today, and there are a bunch of people who have questions about black holes, and we haven't touched on a black hole question today. So can you talk a little bit about kind of black holes and what happens in singularities, like what happens to time and space in the center of a singularity, and how can we study the insides of black holes theoretically in the future?
So the interiors of black holes are mysterious. They're invisible. They're immune from observation just by the nature of the beast itself. Nothing can escape. No information can escape. So it's unlikely we're ever going to get an observational insight into the interior of a black hole. And so we're just left with theory. And the theory is limited by the fact that the black hole theory is incomplete, which is to say that our gravity theory is incomplete. The fact that black hole theory, general relativity, predicts a singularity is a problem for the theory. It's telling us that the theory is not up to the task. What it does say, however, the nature of a singularity is that at the singularity, time and space as we understand them simply cease to exist. So this singularity is a point in infinite mass density, and of course that means infinite pressure, infinite density, and that means space really has no meaning. And then because of the extreme dilation of time and the strong gravity at the singularity, time is essentially a meaningless quantity. Time would not flow or operate at the center of a black hole. So the little we do know about singularities theoretically is that they are places that essentially eradicate time and space. However, the real problem is that our theory is incomplete. And so it's going to take a superior theory than even the great theory of general relativity to truly understand the interior of a black hole. Okay, it's a good one to end on, and good range of questions as always. Thank you, and thanks to Matthew for running the session, and we'll be with you in a couple of weeks.
Excellent. Thank you all. It was great to see you. We are going to take the next, I think, 2 weeks off because we have some travel and conferences and other things going on, but we will update our calendar as soon as we have the next live sessions, and I believe we will, the next live sessions that we will have will be in October. So look for those to be out, and we look forward to being with you all again soon.